Hello. Okay. Um, okay. You should see the desktop now and should be able to hear me. Does everything seem okay? People are still coming in. Okay. Okay. Can you hear me? Does everything seem okay?
Yep.
Yep,
Okay.
that's good.
Thanks. All right. Um, okay. As I mentioned uh, on Tuesday, uh, there is the next midterm exam a week from today, and the review problems are. I got them up there last night. Okay. So here the exam is going to, there's some overlap between the last exam. This exam is going to be over chapters 4, 5, and 6 from one of the books and from chapters 3, 4, and 5 in the other book. And it basically is methods, if statements, and for loops. And we did a little bit of if statements and a little bit of methods on the last exam, and there's going to be some more on this exam. And then there's the really new thing is for loops and while loops. Okay, so here's a list of the topics, so you can see what words we're talking about. Method definitions, method call, Boolean expression. This is where this was the part that was kind of a little, well, this is the part that's a little bit overlapped from last test. Boolean expressions and if-else statements. And then nested if statements weren't on the last test, and then while loops and nested for, while loops, for loops, and nested for loops are new. Okay, so this is what the test is about. These 3 chapters in that book and these sections in this other book. And then there's a bunch of problems here. And the most important thing is to do these problems. Make sure you can do these problems. Use these problems to guide you through learning. Instead of going back and just reading and rereading this stuff, start with solving these problems and make sure that you can and solve these kinds of problems. If you have questions about these problems, please ask. Like last time, I won't give you a solution sheet, but I'll answer any questions you have. Okay, so if you ask questions about the problems, you can show me your answers. You can ask me questions about the problems and stuff like that. But I won't put out a complete solution sheet. You can talk to your friends with them. If you work on them with somebody, fine. Work with somebody on them. Talk with people about them. Just make sure you can solve these. Okay, and there's quite a few problems. They're good problems. I think these are good problems. Solving these problems and asking questions about these problems is a good way to really understand this material. So really encourage you to start working on those problems. Do a couple a day. Okay, and let's see. Anybody got any question? Oh, I put another reading assignment up here for next week. We'll probably start talking a little bit about arrays next week, but your real issue is to start, do these. So you may not, if you got time, do the reading. I wanted to put the reading assignment up there so people could see what was coming next. But if this is more important. So spend your time, spend as much time as you feel comfortable on preparing for the exam. If you have any time left over, you could start reading the stuff about arrays. We'll start talking about it a little bit next week. We'll introduce the idea of arrays. They're not going to be on the exam, so we'll start talking about them. And also next week, we can also, if people have questions about these review problems, we can do some of the review problems during class also. We did that last time. Yeah, we could do some of the review problems in class if there's questions. But I wanted to let you know what the next topic was. So I put this reading assignment up there, but your real emphasis is on preparing for the exam. And I also put 2 more coding bat problems up here. I thought those were nice problems. So coding bat, they're a lot like these problems here. They're very good. Coding bat problems are really good. They really let you know that you're understanding what we're doing. Like this is one of these is a logic problem and one is a string problem. And string 3 were the problems that use strings in 1 or 2 for loops. They don't, like this one I don't think needs 2 for loops, but they could need 2 for loops. So string 3 are the third group of string problems. So they're a slightly harder group of string problems, and a logic problem from the second group of logic problems. Okay. And if you have any questions about any of those, please send an email or come to office hours and ask. Okay. Anybody got any question about anything that's outstanding at this point? Anybody got any question about stuff? Any questions at all about anything so far? Okay. Um, we're going to talk about we've been talking about methods. Okay. So we're going to keep talking about methods. Now, we had this outline. Oh, where is it? Of the words we're using when we talk about methods. Where did that go? Oh, did I forget to put a link to it? I thought I. Oh, I forgot to put a link to something. In class the other day, we made a. I'll put it. It's on the other class's website. So let me just open it up to show you. I didn't realize I forgot to put a link to it on this website. We made a list of words that we're using when we talk about methods. Okay, so we made a list of words like this, and we talked about, and that list is kind of here too. See, it's duplicated in here in the list of words for the review. And what we haven't talked about is this method return type and return statements. That's something we haven't said a whole lot about, okay? Return type, return statement, and return value. So notice in this outline of method stuff, there's this mention of a method return type, a return statement, and a return value. That's what we haven't really talked about real well. So that's what I want to talk about today is this one aspect of methods. Okay. So I've got some examples. They're not on the website yet. I've got them. Well, they're on the they're up on, if you want to see them, if you want to download them, they are on the other. Right now they're on the Monday Wednesday website. I haven't put them up on ours yet, on this one yet. So huh. Oh, that's Tuesday, Thursday still. I'm sorry. No, I'm mixed up. I may have forgotten to put it up here too. Okay, so so let's look at these. I've got the examples here on my desktop, and it looks like I forgot. I didn't put them up on the website yet. Okay, so they'll be up there after class. So they're examples that have method return type, method return statements, and return values. Okay, so here's a folder. Here's an example in it. So I'll put these examples will be up there after. Try they're not up there now. I thought they were. Okay. All right. So let me start Dr. Java. Okay. Okay. Now, the idea of what we're going to do is motivated a lot by the formulas you learn in math class. Methods are a lot like formulas. One way to think about them, it's a lot like formulas in math class. I think this is kind of a good way to approach what's going on here. Okay. So here's a formula from a math class. It's a function that you could graph, you could take the derivative of, you could take the integral of it. So it's a typical formula you'd use in an algebra or calculus class, x squared plus x. Okay, so this tells you what the formula is. The function takes in a variable, and then it squares the variable and adds the variable to the square of the variable. Okay, that's the definition of the function. But then somebody could say, well, what's f of 3? Well, what that means is you take the 3 You plug it into the x, so then you get 3 squared plus 3, and that gives you 12. So you plug 3 in and you get 12 out. If you plug 0 in, you plug 0 in here, 0 squared is 0, plus 0 gives you 0 out. And if you plug 5 in, you get 5 squared, which is 25, plus 5 is 30. So this is what you plug in. This is what you get out. And what you plug in is into that variable, okay? So we call this a function definition. And in programming, we call that a function call. And it returns a value to us. Now, in algebra classes, they don't use this word. They don't use these words. Algebra classes don't talk about a function call. They don't talk about a return value. But they do this all the time. You plug in 3, you get out 12. You plug in 0, you get out 0. So they just use words like you plug in 3 into the function and you get back 12. In programming, we call that plugging something into the function is a function call. You're calling the function. It's kind of a weird, I don't know why they use the word call. Actually, some more sophisticated programmers call it a function application. The more modern word is to call it, I'm applying the function. See, there's the definition, and I'm using that definition. So I'm applying that definition to the input 3. But most programmers don't use the phrase function application. They use the word function call. That's the more common these days. So function application is probably a little bit better because calling doesn't really, the word call doesn't make sense here. You don't call up that function like you call someone on the phone, but you do apply this formula to that input, okay? Right, so programmers call this a function call, and they call this the function definition. Now, here's this thing turned into Java. So I've taken this and I turned it into Java. Notice it turns into a lot more lines of code in Java because Java is trying to be much more than just mathematics. Okay, so first, here's the definition part. Okay, that's this. That's just this. So here's what I'm saying. I'm going to define for you a function f. That's the name of it. And it takes in an x. But in Java, I have to tell you what kind of variable x is. So I have to put a declaration in front of the x. So it's just like this, but I have to tell you what kind of variable x is. So f takes in an x that's an int. Then I tell you what kind of answer it's going to give. This is what we call the return type. So in our list of words, over here's the list of words. This thing here that's sitting in front of the function name is the return type. See, the function this line is called the function declaration. This whole thing is called the function definition. This whole thing is the function definition. This first line is the declaration. The declaration tells you something about the function. I'm trying to highlight that line. Dr. Java won't let me highlight that line. There, just drag across. Okay, that line by itself is called the function declaration. The braces hold the function, the method body. You put the declaration together with the body, and that's called a method definition. The declaration tells you the name, the input variable, the name of the input variable, the type of the input variable, and the type of the return value. It also tells you this other stuff, which we haven't told you what it means yet. Now, the declaration also includes some other stuff here that we're not really saying what that's there for yet. Okay, so the declaration is a name, the parameters, which each have their own name and a type, and the return type. What kind of answer does the function give me back? Just like here, we know that. Now here, in calculus class, can you tell me why they don't need a thing here that tells you what the type of x is? Think of it. Why don't they want that there? Why do mathematicians not bother with putting anything here to tell you what kind of thing X is?
Because it's a number.
And what kind of number in particular?
Double.
Yeah, what we call double, decimal numbers. Yeah, they're never anything but decimal numbers. They don't have other types. They only have one type. They do have integers, but they're not a special. The integers are just a special case of the double, the decimal numbers. And you don't very often have functions that only take integer inputs. Occasionally, a good example that's the factorial. You know, if you've had calculus, you may have seen the factorial function. That's one example of a function that only takes in integers. That's one of the few examples of a function that only takes in an integer. For the most part, the functions take in doubles, okay? So you don't need this. But our functions can take in ints, they can take in doubles, they can take in strings, like here's one that takes in a string. So we have lots of choices for what X can be. Some functions might take in strings. Some might take in ints, doubles, whatever. So I need to tell you what kind of thing X is. Similarly, I have to tell you what kind of answer it gives back. Now, I don't tell you what kind of answer this gives back because just like its input is always a decimal number, its result is always a decimal number. Okay, so I don't need to tell you what kind of answer to get, just like I don't need to tell you what kind of input. So math doesn't need something saying what the answer is, and math doesn't need something saying what type of input it is. The type is always double or decimal, and the real word we use is real numbers. We call them real numbers in calculus. If you look in your calculus book, the X is always what's called a real number, which is just a fancy way of saying a decimal number. Okay, all right. So math formulas don't need that extra bit of jargon. They don't need the type for each parameter. They do need a name. You need to tell me what the name of the variable is. For example, if I write this, I've got a little bit of a mixed up function. You know, you might really wonder what's going on there. Now, to give you a better example, think of this function here. Notice I've got a variable over here, and I've got 3 variables over here. Why don't I put the other 2 variables over here?
Because they're constants, they don't change with the value of X.
Exactly. They're in your math class, that's the slope of the line. So it's just fixed. The line has that slope. That's the y-intercept of the line. Now I could do this, and now I've got something that you haven't studied actually in calculus. Actually, you've never studied that. This is a function of 2 variables, and it's got one constant over here. Now it's got 2 variables. It's not a line anymore. mx plus b is not a line if you make the m a variable. Okay, now it's something else. Okay, it's not a line anymore because now I've made x an input variable and m an input variable, and now I've got a function of 2 variables. Okay, so we in a math class, the variable, you do have to give this thing a name. See, for over here, if I change the name to b, I've got a different function of 2 variables. Now m is back to being a constant because it's not declared here. M is an input variable and b is an input variable. Okay, so and it's not a line. It's a plane. This one is a plane. If you graph this, it's a flat plane. If you graph this one, it's not a flat plane. Okay, it's more of a parabola-like thing. Okay, so I'm sorry. This one, if you graphed it, would be more bowl-shaped, more parabola-shaped. This one, if you graph it, is a plane, and this one's a line. But you have to tell me what m and b are. Okay, so even in math, you got to tell me the name of the variable, because over here, your formula can have other names. Okay, yeah, your formula can have other variables in them, but if there's a letter here that's not here, you think, oh, constant. You tell me ahead of time what it is, and that's just a name for the constant. Like maybe the slope is 5 and the b-intercept is 2. Okay, so now I know what line you're drawing. you're drawing the line with slope 5 and y-intercept 2. Okay, because I wrote what M and B are. Okay, so that I have to tell you the name of the variable. Oh, and if I put an M here, funny thing is, now what is that? Can you think of it? What am I graphing now? A little bit tricky, but nobody's going to do this to you in a math class, but they should. What am I graphing now? Ignore this part here and here. G's got one input. There's the input. The input's multiplied by x, then you add b. But x is not an input anymore. So what is x?
Constant.
It's a constant. Yeah. So mx plus b with m as the variable, x is a constant, b is a constant. What am I graphing?
Line.
Line.
A line. But I've now labeled the slope what?
X.
X. Nobody in a math class would ever do that to you, but they could. There's nothing to stop them. That's the equation of a line with slope x, y-intercept b, and the independent variable, the horizontal axis is the m-axis now, not the x-axis. The only reason they don't do that in the calculus class is they're trying not to confuse you, but they're not actually doing calculus students any favors by not confusing them, because as soon as the calculus student gets into a biology class, the equations start looking like the following. And math students get confused as heck because they get into an econ class or a biology class or a physics class, and the professor says, I want to graph a line, beta times alpha plus t. And the math student says, but my lines are all mx plus b. And the professor in the biology class says, well, m doesn't mean anything to me. X doesn't mean anything to me, but beta is something I measure in my problem. Yeah, beta is something, alpha is something, and t is something. T might be time. Alpha might be a concentration of something. Beta is a concentration of something else. So in the real world of actually using math, mx plus b is pretty rare, but lines are real common. People use lines everywhere in every branch of science all the time, but they don't like the letters mx and b because they don't really mean much to them. They tend to use whatever letters mean something to them. Things like they might say C for concentration, and this might be V for volume of fluid, C for the concentration of something. So G of C is volume times concentration plus time, something like that. They'll use letters that tell them the thing they're talking about. Okay, so you really need to be able to deal with somebody saying G of M equals mx plus b, but that's an equation of a line where the variable's m and the slope is x and the y-intercept is b. Okay, so you always name the variables. Okay, and Java is the same. We give a name to the variable and we do it up here in the declaration. We tell you the name of the variable and the type. Okay, now over here, after you've got the name of the function and the name of the input, you put an equal sign and say, okay, and here's what it does with its input. So here's where you say what the formula does. Okay, that's the body of the method. The body of the method is what it does. Notice there's no equal sign here. Instead of having an equal sign, as if math professors would put a brace there and a brace there. That's more Java-like. F of x is x squared plus x. See, but that's not as nicely to read. That's not as nice to read. You might ask, why didn't Java people use an equal sign? Some programming languages do. Some programming languages do use an equal sign here to say that the function equals, and then down here you have the body. But Java didn't do it that way. Okay, so Java doesn't use the math equal sign, but it's still doing the same idea. You have to tell me what the formula, what the function does with its input. What calculation does it do? Well, that's here. What calculation am I going to do with that input? And here, just for the heck of it, I said, well, I'm going to first compute x squared. And I create a local variable to hold that temporary result. See, that's over here under method bodies can have local variables. So I could put a local variable in a method body if I want to hold temporary results. You can't do that in a math formula. In a math formula, you can't somehow create temporary variables. There are no local variables. This is one of the reasons why Java uses braces, because you want to have lots of lines where you could say, here's a local variable, here's an intermediate step. You're allowed to do intermediate steps in a Java method. In a math formula, there's no notion of intermediate steps. You just say, here's the final answer. So that's why you can sometimes get really long, complicated formulas in math, because everything has to be spelled out in one formula, no matter how complicated it is. Java lets you break things down if you want. So here I can say, do the squaring first, give it a name, then take that value and add x to it. So I'm still doing x squared plus x. I'm still doing the same formula, but I broke it up into two steps. Now here is the return statement. The return statement says, here's where I'm stopping my calculation and I'm giving the caller the final answer. There's no notion down here of a return statement. This is just, since there's only one thing here on the right of the equal sign, the whole thing is the return statement. But here, I'm allowed, in fact, we'll see in a while that you could have multiple return statements. You could have an if statement that says, well, if the input looks like this, use this formula, but if the input looks like that, use some other formula. Okay, so you could have multiple return statements, and you could use if statements to choose which return statement you're going to use. So the return statement says, here's the answer I want to give back. That's this thing here. That's the return value. This is a return statement. This is the return value. That's what I'm returning. That's the return value. Okay, I'm going to give back that answer. Okay, all right, so all of this is that line there. Then down here I have things like f of 3, f of 0, f of 5. Well, that up here in my main method, I'm going to use this function. So down up here I have an example. I have a variable w, which is 1 plus f of 3. So there's a method call. There's one of the method calls. We know that that's going to give me back 12. 12 is going to be added to 1. W is going to end up being 13. So there's a method call. Here are two method calls in one line of code. I call f with the input 3, keep that value in a temporary variable or something else. Java's got to remember that answer. Then Java has to go over here and say, okay, now compute that function, to make the function call with a 4. Then you got those two answers, and then you could do this sum. After you've done that one and you've done that one, then you can add them together and put the result in W. Okay? All right, and then here's a funny example. This is something we call function composition. Take 5 and call f with 5. Then you get an answer. And you take that answer and you call f again with the answer from that call of f. So we work from the inside out. There are two function call here. This is called a method composition or function composition. In calculus, if you're in the calculus class, this is what the chain rule is all about. Chain rule is all about finding the derivative of an f of g of something or an f of something. That's where we use the chain rule, function composition. Okay, so here I've got an inner function and I call it first. I get an answer, then I call the outer function. We do this all the time in programming. We're not doing calculus, but we do method composition all the time in programming. Here's just more composition. I have first I plug 6 into F, I get an answer, then I call F again with that answer, then I get a second answer from F, then I call F a third time with the answer I got from the second call of F. So the output of each call to F becomes an input to the next call of F. Then the output of that call of F becomes an input to the next call of F, and the output from the third call of F goes into W. Now, what we're talking about now is this idea of the flow of control. The idea that what's happening is, for example, take line 6. The flow of control is, first I got to jump down to here and compute F of 3. Come back up here, hold that number, go over here, now jump back down here, compute F of 4, go back up here, take the two numbers I got, add them together, and store it in F. That's the flow of control. And we're going to use the Java visualizer to watch that in a second. Okay, that's the flow of control in these things. That's what we want to show next. That you actually have to jump from here down to here, do the work, jump back up here with your answer, then go to here, jump down here, do some more work with a different argument, different input, then go back up here and finish the result. Okay, so this line of code is actually 1, 2, 3, 4 steps. There's actually, from the point of view of the Java language, 4 steps to doing that line of code. Step 1, compute F of 3. Step 2, compute F of 4. Now I've got two numbers, so step 3, I can add them. Now I've got an answer, and step 4 is put the answer in W. And we'll see that in the Java visualizer. That's one of the things we want to do, is go to the Java visualizer and watch these things take place. Okay, so let's take this example now. Let's move it up to the Java visualizer. Oh, we could watch it in, remember we saw how to watch things happen in Dr. Java with the debugger, but it's a little bit easier. I could use the debugger to watch these steps, but right now I want to jump to the Java visualizer to watch them instead. It's because it's just so much easier to use the Java visualizer than it is to use the debugger, than it is to use the debug mode in Dr. Java. Okay, so I'll go to, where's my, oh, okay. Okay, I want to go to the Java visualizer. Okay, I'm going to plug our code in place of that. Okay, and now I want to watch this thing happen. Okay, so, okay. And as we watch it, we want to pay attention to the terminology over here. We're going to keep talking about these words as we watch things happen over here. Okay, so I start on line 5. I need to do this before I can do the addition. So I'm going to jump from line 5 down to line 13. Okay, now what happened here? That argument, that's one of our words. In a method call, we have an argument value in the method call. The argument value is going to be put in the parameter variable from the method definition. The visualizer shows that for us. The 3 from there got put into the X here. So see, I'm in F, line 13, X got 3. Okay, here it's called an argument, and here it's called a parameter. So the method has this parameter. The value of that parameter came from this argument. Okay, so this variable didn't get a value until I called the function. When I call the function, X gets a value. Okay, so X is 3. Then, okay, now I'm on line 13, and I create the local variable. See, I created the local variable which holds X squared. Now I'm about to compute 9 plus 3, which is 12. And see, the Java visualizer says you're going to return 12. So now 12 is what's going to get returned to line 5. See, this is the stack diagram. That's another one of our words. See, we're looking at a stack diagram. The stack diagram shows us that a method called main at line 5 of main called the method named f. We're currently at line 14 of f, and here's our variables. We've got 2 parameter variables and we have 1 parameter variable and 1 local variable. This guy's actually a parameter because he's declared up here, and this guy's a local variable because he's declared in the body. If you're declared in the declaration, you're a parameter. If you're declared in the body, you're a local variable. That's the definition. That's what these words mean. So a local variable is a variable that's declared in the body, and a parameter variable is declared in the method declaration line. Okay. All this terminology makes it, in the long run, it makes it easier to talk about programming. It's a lot of words to learn. It's like you're learning a foreign language, and you're learning a technical language. It's like studying physics. When physics, you got to learn, what's momentum? What's angular momentum? What is gravity? What is a force? What is friction? You have to learn what all those concepts mean. Well, programming, to let us be able to talk about programming, we have a vocabulary and we use it. If you talk to programmers, they're using these words all the time, because otherwise it's real hard to talk if you don't have very precise words for things like an argument value versus a parameter variable, because one of them lives over here in the function call and one of them lives down here in the function definition. Real important. They're really different. So argument value, parameter variable. But when you make the function call, you pass the argument to the parameter. Okay, and we see that here. So these words make it a lot easier to talk about this stuff and to make sense out of it. Okay, now I'm about to do the return. So I'm going to return from line 14 to line 5. Okay, I'm back at line 5. Oh, look what happened over here. What just happened? Go back, line 14, go to line 5. What's important that happened?
Variables again.
The method is over with. So all its variables are erased from memory. All these variables are erased because we don't need them anymore. The calculation is done. The return value is going to be sent up here, and all this stuff here gets erased. So that's the stack frame. That's part of this idea of the stack diagram. When you do a method return, the stack diagram for the method goes away, and you're left with just the diagram of the method that you're in. So notice that right now, main is paused at line 5 while this does its work. While this guy's doing his work, there are 2 frames over here in the stack diagram. One for F that's working and one for main that's paused. When F is done, we're back to working in main. So this is the one at the top and F is gone. So the one at the top is the one we're working in. We're working in main now. We've got an answer here. It doesn't show up in our picture, but we've got an answer there. The answer was 12. So it doesn't show you that here, but there's a 12 there really right now. Okay. Now I haven't finished line 6 yet because there's still the addition to do, and there's still put a number in W to do. So if I click forward, those 2 things happen at once. Okay. It does not show you the addition as being one step and the putting in W is another step. But later on, you'll see that they really are separate steps. When you study the language in a little bit more careful detail, you'll see that there was really 4 steps here. Step 1 was do that. Step 2 was do addition. Step 3, well, there was 3 steps here. Step 1 was do that. Step 2 was do the addition. And step 3 was do the assignment. Put the number in W. The visualizer only shows it as 2 steps. One step was doing this, and the other step was doing all of the rest, was doing the addition and putting the answer in W. So if I go back one step, what now, I've got that answer there. I don't see it in the picture, but the answer is there. Notice that W doesn't even exist yet. I'm on line 5, but W doesn't exist yet because I'm still working on the right-hand side. I click forward one last time. Oh, and W appears now. It's got the answer 13. So the 12 from there was added to the 1, and I've got a 13 in W. Okay, now I'm at line 6. Now, line 6 is going to be 4 steps. Do this, then do that. Notice I don't go from left to right. Well, I go from left to right, but I skip over the plus because it can't be done yet. Do the F of 3, then do the F of 4. You've got 2 answers. You can do the plus, that's step 3. Then you can put the answer in W. So first, we're going to do this guy. Now we know we're doing that guy because we're down here, and our argument is 3. So that means we did this guy here because the argument is 3. See, x is 3. So I'm going to do this calculation. I'm going to return 12 up here. 12 is going to return up here. I'm back up here. Now, I don't see the 12, but there's a 12 right there. But now I have to do the next step. I'm back down here, but I'm really now over here, and I come back down here. How do I know I'm over here? Because there's a 4 as the argument. So I'm back down here, going through the method again. I'm about to return 20 to here. Okay, now I'm back here. There's a 20 there and a 12 there. So now I can do the next step of adding them, but the visualizer won't show that as a separate step. But the next step is adding them. Then the next step is changing what W is. If I click forward one more time, I think it's just going to show W changing in one step. See, it doesn't show me 2 steps. It shows me 1 step. But it really is, later you'll see that there really is 2 steps. Do the plus, then do the equals. Calculate 12 plus 20, get 32, then put 32 in W. Okay, all right. Now let's go, now we're ready to do line 7. First we have to do the inner thing. So now we're down here with the argument 5. Because we really came from, we're doing this part of line 7. See, we're from line 7. See, we're coming from line 7 with argument 5, which means we're doing this inner part here. Do the calculation. I'm going to return 30. So 30 is going to go in that slot there, even though it won't show me that. Okay, 30 is there. But now I have to call F again. So I'm going to call F, and notice there's the 30. See, 30 became the argument for that F. The 30 that was the return value from the inner F is now the argument to the outer F. The return value from the inner F became the argument of the outer F. So again, I'm using all these words here. The return value from the inner F became the argument for the outer F because I had F of F. Okay, this guy's return value is this guy's argument. Okay, now I'm down here, click forward, forward. I'm going to return 930. Now 930 is actually going to be put in W. So I'm going to come back up here. There's a 930 there, and it's just going to be put in W. So I'm going to see W update now. So one more step. I've finished the right-hand side now. Now I need to put it in the left-hand side. So one more step. W's got the 930 in it now. Now I'm at 8, and I won't go through all the steps. This is just going to do, it's going to do 3 calls to F. So we can just real quickly watch them. There's 1 call to F, back to 8. There's another call to F, back to 8. There's our 3rd call to F, back to 8. Now, the third call to F is returning that big number there, 32,000 something. No, is that 32,000 or is that what? They really ought to put commas in these numbers. That's 3,200,000 something. So that's like 3 million something. So the 3rd call to F returned 3 million. So 3 million something is right there. and it's about to be put in W. One more step, and it got put in W. So we watched the flow of control with the argument values being put, what we call, the argument values are passed to the parameter variables. So every time you have a function call, you have an argument value, which gets put in a parameter variable, and we call that passing argument values to parameter variables. We've watched the stack diagrams, and we've looked at what the actual return values are. Okay, now let me play another game with this example. Here is formula where I did a funny thing. Java lets me, I can break up lines any way I want. I can't do this in Python. This would drive Python crazy. But Java doesn't care where you indent. Java just doesn't care about indentation. So I can put this, this, and this on separate lines. Now that ends up tricking the Java visualizer into showing me where it is in, like here, when we were on, if I back up a bunch, I'm going to back up to line 6. Oh, okay, I'm at line 6. Where am I in line 6? I don't know, because I've just been doing a bunch of clicking. I don't know right now if I'm here or here, because the Java visualizer just shows this as line 6. By doing this trick, the Java visualizer will show me whether it's at this line 11 or this line 13. I wish it would show you when it's on line 12, but it doesn't. It does not distinguish line 12 from by itself. It will show me when it's on line 11. It will show me when it's line 13, but it won't show me when it's actually at the step of line 12. Okay, but it'll show me this one versus this one. And for like the function composition, it'll show me when it's doing this one versus when it's doing this one. So let's copy this up to the visualizer and just real quickly do the same example that we did here, but we'll see that the visualizer is kind of fooled now into showing us a little bit more information. No programmer would write their code this way. This is just a trick for getting the visualizer to kind of show us the order of the steps. Now see, I tagged the steps by their order. When you do this, step 1 would be to do that function. Step 2 would be to do the addition. Then step 3 would be to finish the assignment. In this one, step 1 would be to do f of 3. Notice the order, step 1, step 2, step 3, step 4. Notice how you're jumping around. That's why it's important to understand how this stuff, you don't read it from left to right. Step 1 is do this. Then step 2 is do that. Then step 3 is to add the answers. Then step 4 is to put the answer in W. If we visualize this, we see this kind of happen. Okay, we're at line 5, but what does line 5 do? Nothing. Line 5 transcends us to line 8. See, line 5 has to send it to line 8. Line 8 is going to send us into the method down here. Down here, we're going to compute the return value. We return to line 8. Now, we should go from line 8 to line 7, but the visualizer doesn't know that much detail. So it goes from line 8 to line 10 and just did step 2 and step 3 as one step. Okay, so here I'm back to line 8 after doing the function call. I should go to line 7 and do the plus, but the visualizer isn't that smart. So the visualizer, and then I should go from line 7 to line 5 to do the equal sign, but the visualizer doesn't show those sub steps. So I go from here to down here. Okay, now I'm at line 10. Well, I need to start this formula. So I have to go first to line 11, because that's step 1. That's going to take me into the function. The function is going to return 12. 12 is returned to line 11. I'm done with line 11. There's a 12 there now. So now I got to go to step 2. And now I can see that it goes to step 2. Okay, so now I'm about to do this. This is going to go down to down here. It's going to return 20. So I return 20 to step 2. So there's a 12 sitting here, a 20 sitting here. Now you could do step 3, but the visualizer doesn't show you that. So next would be step 3, which adds 12 to 20. Then step 4 would be put the answer in W. It's just going to show those step 3 and step 4 as one click. See, W got updated. So in one click, I went from step 2 to being done. So in one click, I did step 3 and step 4, and then went to the next line. Okay. Now here, again, I need to do this. I need to evaluate this right-hand side. I'm going to start in line 17. I start with the inner function. So I'll see at least that I jump to the inner function. That takes me into the function here. I get my return value. It's going to be 30. My return value, now notice that this is returning. The visualizer actually returns to step 2, which is kind of interesting. It didn't return to step 1. It actually returned to step 2. It's kind of quirky about sometimes where it returns to. A lot of times it returns to the line it came from, but sometimes it chooses to return to the next line. So I'm returning 30, and it returns to step 2, which makes sense. After step 1 should be step 2. Okay, so now a 30 is right here. And I'm going to do this function call with the argument of 30. So step 2 is going to lead me back down here. There's the argument of 30 inside the function. I'm about to return 930. Now I'm returning 930 to step 2, but I'm not even sure where it's going to return it to. It could return to step 2. It could return to step 3 because it's about to use. It should now take the 930 and put it into W. Okay, so it returns to, okay, shows me returning to step 2. The 930 now is right there. And then the next step would be, now it's not going to jump to this line. I'm going to click forward one more time. It's going to finish step 3, but it's going to take me to the end of the function. It's not going to take me to line 15. Okay, so it finished step 3 and just jumped me to line 19. The Java visualizer is very nice, but if they worked a little harder, they could make it be much more careful about showing you exactly these steps. I mean, that would be something they could do to make a tiny improvement on it. Dr. Java, I don't think does this any better. I don't think it shows you these steps any better than the visualizer. In fact, I don't even know if it shows you these steps at all. I haven't tried doing this trick here of trying to force the visualizer to show you the steps. I haven't tried it in Dr. Java. So I don't know if Dr. Java actually will jump around these sub-steps any better than the Java visualizer did. Okay? But it's still pretty good. Instead of just sitting on that line over and over and over again, or sitting on that line over and over again, wondering where you are, or sitting on that line over and over again, wondering where you are, by breaking the line up like this, you know when you're here and when you're here. At least. You don't know necessarily when you're here, but at least you know when you're here and you're here. So we see the flow of control, which is important. It's an important thing to see that flow of control. Okay, let's do another example. This is a little bit more sophisticated. Formula 2, the math formula, I want to do another example. I'm going to change a couple things. First of all, I'm going to use doubles as my x and y. So my functions will, just like in math, they'll take decimal numbers. But my function is going to take in 2 numbers, x and y. It's going to take 2 times x, 3 times y, add the answer, and add 1 to it. That's what my formula is going to do. And then here's the formula in Java. Here's the formula in math. There's the function definition. Here's the function definition. G takes in an x that is a double and a y that is a double. If I wanted to, these could be different types. I could make this a double and this an int. Probably wouldn't be very useful in this case, but they don't have to have the same type. So the x is a double and y is a double. I'm going to give back an answer that's a double. That's my return type. Notice math doesn't need to say that. It's just taken for granted. decimal number, giving you an answer that's a decimal number. But here I have to say decimal number, and answer is a decimal number. For example, if I wanted to, I can make the answer here an int. By rounding, I could round this number off to an int before I returned it. So if I wanted to do something kind of quirky, I could take in two doubles and return an int, and then do a math.round before I return the answer. You know, if I wanted to, whatever, if I had a reason for doing that, I don't have to have the return type be the same as the input types. In math, it's always going to be decimal number in, decimal number in, decimal number out. But Java lets us do a lot of things we can't do in a math formula. We can do anything we can do in math, but we can do also other things. So right now, I've got it so that it's going to return a double. Okay. So then now here's a function call. Plug in 2 and 1 for x and y. 2 times 2 is 4. 3 times 1 is 3. 3 plus 4 is 5. Plus, let's see, would I do that wrong? 2 and 1. Oh, I'm sorry. 2 times 2 is 4. 1 times 3 is 3. So 4 plus 3 is 7. Plus 1 more gives me 8. Okay. On the other hand, if I take g of 1, 2, the 1 goes into x. So that's 1 times 2 plus 2 times 3. So that's 6 plus 2 is 8. Plus 1 more gives me 9. Okay. So those are function calls, returning a value. Up here, there's a function call, and its return value then is used to add up a couple more numbers. So I call the function, and its return value gets added to 5 and 3. Here, I call the function once, and I call the function again, and its return value is used to, the two return values are added together. Here's a little quirky one. This is a little bit like the composition here, where I had this inner function whose output is the input to that outer function. Now it's a little bit different. Here's an inner function, but its output is only one of the parameters to the outer function. Since the outer function takes in two parameters, one of its parameters is a 5, and the other parameter is the return value from g of 6, 7. Here's another example. G needs two inputs. One of its inputs is an output from G, and one of its inputs is an output from G, another call to G. Okay. I can even do kind of a weird example. Here's a weird example. Okay, if you read this, what gets done first? You need to compute this guy. He needs his first number and he needs his second number. But his second number is a function call, so I can't compute him yet. I have to wait till I know this answer. G needs a first number and a second number, but the second number is another function call. So I can't compute G until I know his answer. This G, so there's where I start. See, I start with G of 3, 4. So I do that one. No, and if you count parentheses, that's the innermost set of parentheses. So if you in math, you always do the innermost parentheses first. And if you look at the parentheses, the way they're balanced, that's the innermost. So I do this guy first. Then when I have that answer, I can work my way out a little bit and I can do that guy. Then when I have that answer, I can finally finish that one. Okay. So notice that this is 3 G's and this is 3 G's, but they look very different. This one, do this G, then do this G, then both of those answers go into this G. Here it's, I want to do this one, but I can't yet. I want to do this one, but I can't yet. So I do this one. Now I can do this one. Now I can do this one. Here is, I want to do this one, but I can't yet. So I do this one. Then I do this one. Now I have the answers, so I can go do this one. So there's slightly different orders to it. That's the flow of control. That's the order that we do the calculations in. And with the Java visualizer, you could watch these things happen. Okay, you could watch that this came first, followed by this one, followed by that one, versus this one, followed by this one, then those two answers going into this one. Okay, and if you really want to watch them happen in the right order, you do formula 2 with stepped lines like this. Okay, let's put this one in the Java visualizer real quick. And then, you can actually then see how when you get to this one, you do that one, then you have the answer. Whereas here, you have to go to this one first, then you can go to this one, then you have the answer. So let me, okay. A little bit tricky to read this because it's written in an ugly way, but it's written in an ugly way to make it, to show us something. So we're purposely writing code in an ugly way, makes it hard to read, but it helps us see that this is a step and this is a step. Oh, I forgot to put the step numbers here. Yeah, which see, this one is step 1. You do things kind of from left to right. That one's going to be done first. Then this one's going to be step 2. And then the visualizer won't show it to us, but this is step 3. You can do the addition, and then this will be step 4. Okay. And for this guy, you're going to start him down here. You see, you'll start, you can't do this one until you have that answer. So you have to do that one first. Then you can do this one as step 2. And then you can go as step 3, put the answer into W. Okay. And over here, you have to start with the innermost function. So compute that G will be step 1. And then the 5 doesn't need to be computed. It's just sitting there. So once I've done step 1, I can then do step 2. And then after I know what the result is from the addition, then up here, I can do step 3. But the visualizer won't really let me see the step 2 and 3. Okay. All right. Now, okay, let's just step through it. Okay, we're on line 6, but what are we, we just got there. So the first thing to do is step 1. So we see we're on line 6, but we really start with step 1. Step 1, actually, no, oh, I should actually, I didn't even label that right. There's actually more steps than I didn't even, I wasn't thinking. There's actually more steps there. After you have that answer, you do this addition, right? That's step 2. But then you go and then see, then you have to do the additions from left to right. So then there's a step 3. And then this guy is actually step 4. Should have noticed that because there's 2 additions. So they have to be done. Each one is a different step. So after you have this number, you do additions from left to right. Okay. So then step 1, see if I got them labeled right now. Step 1 is compute that number. Once you have that number, you can do this addition from left to right. So that is step 2. Once you've done that addition, now you have the left-hand number for this guy, which is step 3. Oh, and this is not a step anymore. That's what I was, okay. Okay, so then you have this guy's step 3. Now you've done all the additions, so you have an answer and you can put it in W as step 4. Okay, so do the G, then do that addition from left to right. So that addition gets done next, then that addition gets done next. Then I can put the answer in the W. Okay, so there's really breaking it down as G plus 5 plus G of 2, 1 plus 3. You need this guy. So you would do the addition from left to right, but this addition can't be done without this answer. So I'm forced to do this answer first. Then with that answer in hand, I can do the addition. Then with that answer in hand, I can do this addition. And then with that answer in hand, I can put the result in W. Now, the visualizer is only going to show me step 1. So let's go to visualize. It's only going to show me step 1. Okay, step 1. Step 1 sends me into the function. The function is going to return 8. So 8 is returned here. Okay, now there's an 8 sitting there. Okay, now there's an 8 sitting there, 5 plus 8 plus 3. It should be go to this line, do that addition, go to that line, do that addition. But the Java visualizer is not going to show me that. It's just now if I do step, it's going to just put the answer into W. See, put the answer in W. So it went from step 1 to the next line. But as you learn more about programming, you learn to really think of these sub-steps. They're really there, and you'll actually see how to see them later on. With more tools, you can actually see that that's a step by itself, and that's a step by itself. Okay, so that's the flow of control. We need that answer before we can do that. And then once we have that answer, we can do that. Okay, now what about here? Okay. There's only one addition. That addition needs its left-hand side and its right-hand side. You can't do the addition without the left and right-hand side, so we'll start with the left-hand side. So we're first going to start with step 1. Step 1 sends us into the function. It's going to return 9. So now there's a 9 there. There's really a 9 there. We've done step 1. Well, now we have to jump to step 2 because we can't do the addition yet. So we jump to step 2. So that's going to send us into the function again. We've got the 3 and 4 as the arguments. The argument values got passed into the parameter variables. Okay. So 3 and 4 got sent to y and x and y. We do the calculation. We're going to return 19. So 19 is going to get here. So now there's a 12 here and a 19 here. Now, there are 2 more steps to do. Do the addition, put the answer in W, but Java Visualizer, I'm going to click one time, it's going to do both those steps. So step 3 and 4 are just going to get conflated, and I'm going to get the answer in W. There's the answer in W, and I'm ready down here. And in here, now I see, okay, I want to compute W. Well, W is the result of this, but the result of this can't be done until I know what the other argument is. See, I need that argument before I can call that function. So I have to compute that argument first. So that's step 1. So I jump to step 1. Step 1 sends me to the function with those 2 arguments, 6 and 7. Return value is going to be 34. Now notice that there's a 34 here, but it showed me returning to step 2. So here's one of those quirks where instead of returning to this line, it returned to what was going to be done next. So it just jumped straight to step 2. So now here is a, what did we say it was? 34. A 34 is right there. That's one of the arguments. So now G needs to be called with arguments 5 and 34. So click forward, and there's the arguments, 5 and 34. Remember, that 34 was the return value of that guy. So that guy's return value became this guy's argument. So once again, we see that one function's return value became another function's argument. Okay, now we're going to return 113. So 113 is that. All that's now 113, and we're about to put 113 into W. So now the last step, put 113 into W, that was step 3, and we're done. Okay, so the visualizer let us see these micro steps, these little steps. We're really watching the flow of control, and we're watching the stack diagrams, and we're watching the return values and how the return values sometimes become arguments when we do composition. When we have a function of a method of a method, then we see that the return value can become an argument value. Not always the case. You know, when you have like here, the return value is not an argument. The return value gets stored in that variable. But here, the return value is an argument to there. Here, the return value is an argument to plus. And here, the return value is an argument to plus. But we don't see that in the visualizer. But this return value is an argument to that plus, and this return value is an argument to that plus, and plus's return value goes into the variable. It's the return value from plus. Plus is just another method. It's just a method that's built into the language. It's just another function built into the language, and its return value got put into W there. Okay. All right. We're going to see one. We're done for today. We've run out, finished time. We've got one more idea to do, and I'll just show you real quick what it is, and we'll talk about this next week. We need to realize that return and print are not the same thing. This is a real common mistake among beginning programmers, that when they write a method, they think the method should print its answer. And printing an answer and returning an answer, notice that what it's returning here is exactly what it's printing here. They are really, really, really different ideas. And you're going to have to fight with yourself to remind yourself that there's a big difference between returning and printing. Among beginning programmers, it's one of the most common mistakes to make, of mixing these two ideas up, because you want to see the answer. So the quickest way to see the answer is print it. But then that gives you a false sense that when you see the answer, you're returning the answer. And we'll do this example here, and we'll see why that this and this mean very different things. Notice that this function returns a double. This function doesn't return anything. That void there means I'm not giving back any answer. That's a problem, because what it's going to do is means that this function can't be composed with other functions, because we saw in a minute ago that a function return value becomes an argument to another function. An argument return value, a function return value is an argument to another function. That's crucial. And that breaks when you do this printing thing. There is no return value. Okay, so that's what we'll pick up next week. The distinction between returning answers and printing answers. They're easy to mix up because they both show you an answer, but this one shows you an answer in a way that's pretty unusable. It's really not very valuable. This is a way better way to do things. Okay, so that's where we'll pick up on Tuesday. Okay, real important idea that causes a lot of confusion. Okay, so if you've got questions, remember, especially with the review problems, you know, look at the review problems. If you've got questions about the review problems, work on them. You know, if you got questions about them, send me an email. And next week on Tuesday and Thursday, we can look at some of these. And if we have time, we'll start talking about arrays. So if we have time, we'll start talking about arrays. But otherwise, we can look at review problems. Okay. So we'll end now. Have another weekend. It's Halloween, so I hope you can find a way to have an enjoyable Halloween. And see you next Tuesday. Please write if you have questions. Okay. So I'll end the class now, and then let me know if you have questions over the weekend. Bye.